This video focuses on step 4 of building a regression model. Once again, we are dealing with the home sales data set where we have 13 homes in which we've recorded the size in square feet and the selling price of the house. Previously in class on Wednesday, we plotted the data and evaluated it. We saw that there is a strong correlation between square feet and price. It's a positive correlation, and it looks linear. So we hypothesized a model. Y is equal to beta 0 plus beta 1 x1, or price is equal to an intercept plus a slope times the square feet. We use the software to estimate the model parameters. Now when we take a look at a regression report, we're going to find the results of that regression, or the model itself, in two locations. First, right below the report, we have linear fit, and there we see the regression equation. You'll only see this when we're doing a simple linear regression. When we get into a more complex model with additional factors, you're not going to find this. Where we will see the model is under the parameter estimates table, and the parameter estimates table is the third of three tables that are generated initially with a regression report. The parameter estimates table has several columns. We find the model itself in the first two columns, where we see the terms that are in the model, the intercept and the factors, and the estimates for those, or what values those parameter estimates take. So from this, you can see that the model, y, is equal to 2.7 times, 2.7, the intercept, plus 0.0478 times square feet, or x. Once we have the model, we have to determine whether it is a good model, and we're going to do that in two steps. First, we're going to take a look at the parameter estimates themselves to see whether they are statistically significant, and then we'll take a look at the form of the model and verify that a linear model is the best model to use. Now, when we think about the parameter estimates themselves, we're actually running a hypothesis test, and we have two hypotheses that we need to set up: null hypothesis and an alternate hypothesis. The null hypothesis is that there is no relationship between x and y, and if that's the case, the slope is going to be 0, and that gives us a model where the best guess for y is the average value of y. In other words, x doesn't play into this. Alternate hypothesis is what we came up with in step 2, a linear model. Y is equal to intercept plus a slope times x. Graphically, what are we looking at? We have our data set. Our null hypothesis is that y is equal to y bar, and here is y bar. So this red line that we're looking at is the null hypothesis. Alternate hypothesis is the green line. Y is equal to an intercept plus a slope. And under this model, y varies as x varies. So this is our alternate hypothesis. Now, the regression report gives us three tables. We've got the summary of fit table, and in that summary of fit table we have our r squared, our coefficient of determination. And remember that that coefficient of determination is the square of the correlation coefficient. When we take a look at that correlation coefficient and find a high correlation, well, we can get a pretty good idea that we're going to have a significant model, and that we're going to reject that null hypothesis. But we actually run the hypothesis test in the analysis of variance table. Now, the analysis of variance table has a number of different parts. It has sources of variance, it has degrees of freedom, sums of squares, mean square, and finally an F ratio. The F ratio is the result of the table, and that is the statistical value that we are testing. An F ratio of 68 is our test statistic, but without having F-tables and a little bit of time to go through those F-tables to make a determination, we don't know if an F ratio of 68 is big or not. Fortunately, JMP gives us a p-value for that, and that p-value is very small, meaning that this F ratio is significantly different than what we would see under the null hypothesis. So given that, we reject the null hypothesis. Now let's take a look at exactly what's in this analysis of variance table. Row by row, we've got model, error, and total. What is the total? First off, if we go back to our drawing here, we can measure variance around y bar. In other words, we're taking the simple variance of price. And that is y sub I minus y bar squared over n minus 1. A simple variance. Well, the total variability, or the sums of squares, is y sub I minus y bar, taking these distances and squaring them. And of course, when we square a distance, we're turning it into an area. And that gives us a total sum of squares, 4435, the total variation around price, or the total variability around price. Now, the second one we want to take a look at is this error. And when we measure the error, we're not measuring the error around y bar, we're now measuring the error around our model. You see that the total variability that we had for this point was pretty large. But when you compare this to the model, very small. Some of these are going to be a little bit larger than others, but what we're taking a look at now is the variation around the model, y sub I minus y hat, or the predicted value of y, and we square that. And that gives us 614. So if you think about this, we started with 4435 total variability. After we apply the model, we've got variability of 614, which is a pretty significant difference. And what exactly is that difference? Well, that difference is 3821, the total variability that our model accounts for. So the sums of squares is breaking up the variability in the y. We've got a total variability of 4435. When we apply the model, we eliminate most of that variability, 3821, and we're left over with 614. This total variability, broken up between the model and the error, forms the basis for our statistical test. We're going to take row by row the sums of squares and divide by the degrees of freedom. Now, what are the degrees of freedom? Well, we start with 13 observations, and we lose a parameter, or degree of freedom, for each parameter that's in the model. Our model has two parameters, a slope and an intercept. So we're going to lose 2 degrees of freedom, and that leaves 11 degrees of freedom left over. Now, why does this total not add up to 13? Well, initially we lose 1 degree of freedom for either the intercept or y bar. And under the null hypothesis, the intercept is y bar. So our model is adding an additional degree of freedom to Now, taking a look What exactly do these degrees of freedom represent? Well, we've got 13 observations in the model, n equal 13. However, we lose a degree of freedom up front when we estimate the mean of y, which under the null hypothesis, the mean of y is also beta 0, the y-intercept. So that leaves us with 12 degrees of freedom to deal with in the analysis of variance table. If our model is correct, we're going to lose one additional degree of freedom for the model, for the estimate of the slope. So 13 minus 1 degree of freedom for the intercept and an additional degree of freedom for the slope gives us 11 degrees of freedom for the error term. So 1 plus 11 equals 12, 12 plus 1 equals 13. To get to the mean square, we're going to divide the sum of squares by the degrees of freedom. For the model under simple linear regression, sum of squares and the mean square are going to be the same. For the error, 614 divided by 11 gives us 55. This 55.85 is the mean square error for the model. And you can think about that mean squared error is the variance of the model, or the variance of y about the model. And from the mean square, we get the F statistic by dividing the mean square model by the mean squared error. 3821 divided by 55 gives us this F ratio. Now keep in mind we can't evaluate an F ratio directly. It's hard to say what is large or small because it's based on the degrees of freedom. So we're simply going to take a look at the p-value. And again, what this p-value is telling us is this model significantly better than model of the null hypothesis? No relationship between y and x. P-value smaller than 0.0001 is highly significant, so we can reject the null hypothesis and say that this model is significantly better. Another way of thinking about this is if there is no relationship between square feet and price, we should get a blob of data. Correlation of 0. Now, under that null hypothesis, what we're checking is if the null hypothesis is true, how unlikely is this sample? Is it likely that if the true relationship is simply a blob that we would pull a sample that shows a very strong linear relationship? Not very likely. So that is step one of evaluating the parameters. One last thing I'll point out when we take a look at the parameter estimates table, we can also run a similar hypothesis test on the estimate for 0.04787. Regression software is going to provide us a standard error of that estimate, and the estimate divided by the standard error gives us a t-ratio. T-ratio is something that we can evaluate a little more intuitively. We know that t-ratio greater than 3 is very unlikely. We see that this t-ratio is 8.27, and the p-value for that t-ratio is smaller than 0.0001, highly significant. In other words, this estimate, as close to 0 as that looks, is significantly different than 0. Under the null hypothesis, beta 1 is 0. Alternate hypothesis, beta 1 is not 0. For simple linear regression, if we take 8.27 and square it, we get the F ratio.